All right, here we are for day 10. We are doing okay so far. Haven't really ran into any super stumpers. It was that day 8 one, but nothing that I couldn't solve while in stream. I imagine maybe around day 15, day 20 or so. There might be one or two that may become a problem where I don't really want to stay up all night trying to figure it out. That is kind of the time crunch I'm working against is how late into the night do I want to work on this. So far so good. We are making our way again to some island looking place. I don't know, Greenland? Maybe? Day 9. Day 9, what did we do? We didn't do the opcode stuff as a continuation. Instead, we did a bit of decryption, but this seemed like it was closer to like a earlier day problem. It was okay. These are all interesting problems so far. Another great thing about this is it was run into some interesting ones. Doesn't really focus too much on a singular concept. And I'm already getting tired. But yeah, you don't have a singular concept in most of these, and you often have the opportunity to solve it a few different ways. I'm not a huge CS dude, so often that means I'm taking the brute force approach on these. But so far that has worked out for me. Only had to do, some minor search space stuff. Don't start searching through the entire list every time, that kind of thing. Alright, we're about 10 seconds in. We'll see how this one goes. Okay. We're passed into the data port. The battery is dead. You'll need to plug it in. There's one problem. Charging outlet near your seat produces the wrong number of jolts. Each of your voltage adapters is rated for a specific output voltage, your puzzle input. Any given adapter can take an input 1, 2, or 3 jolts lower than its rating and still produce its rated output voltage. 1, 2, or 3 jolts lower than its rating. It's interesting. In addition, your device has a built-in voltage adapter rated for 3 jolts higher than the highest rating adapter in your bag. If your adapter lists were 3, 9, and 6, your device's built-in adapter would be rated for 12 jolts. Voltage adapter for 3 jolts, higher than your highest rated adapter in your bag. Okay. Treat the charging output near your seat as having an effective voltage rating of 0. Since you have some time to kill, you might as well test out all of your adapters. Wouldn't want to get to your resort realizing you can't charge your device. If you use every adapter in your bag at once, what is the distribution of voltage differences between the charging output, the adapters, and your device? Okay, we have an example here. Your device's built-in voltage adapter would be rated for 22, which is the highest, 3 higher than the highest rated adapter. Because the adapters can only connect to a source 1 to 3 volts lower than its rating. In order to use every adapter, you'd need to choose them like this. Effective rating of 0, so the only adapters that could connect to it directly would have to be a voltage rating 1, 2, or 3. Okay, so we're chaining these adapters together until we get to 22. There are 7 differences of 1 jolt and 5 differences of 3 jolts. Here's a larger example. When using every adapter, there are 7 differences of 1 jolt and 5 differences of 3 jolts. Is that what we need to figure out? There are 22 differences of 1 jolt, 10 differences of 3 jolts. There's no 2 volt differences? One, 2, or 3. Only one you have is an adapter rated 1 jolt, difference of 1. Difference of 3, difference of 1, difference of 1 and 1. Yeah, that's odd. Am I getting a puzzle input that's always going to have either a 1 or 3 difference? Okay, so let's start with a list of adapters. All right, send this to a list. Let's sort it. Let's sort. No. What? Oh, that's right. The sort thing is the weird void. Okay. So we have a sorted list, and then we can basically go through it and just count our 1 and 3 differences. Is that really how it's going to work? What does my list look like? So my adapters, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I really don't have any with a difference of 2. Super weird, but whatever. Let's see, let's count the, I don't know, differences of 1, differences of 3. So we're going to go through each item in our adapters. We're just going to check if it's a, a difference of 1 or a difference of 3 between this one and the next one. Or the previous one, I mean. let's see, I minus 1. Right. What are we doing? Let's just see what we get. So 21 and 9. Is that right? So they said 22 and 10. Why am I one off? Did I not count the last one? I minus 1. Oh. I guess I should count 0. Or maybe just add 0 to the first one? Let's add 0. We get 22 and 9. Why not 22 and 10? Difference. Good old off by 1 errors. Let's see. So my list doesn't include 0. So I've added 0. Oh, and right, I need to add my adapter, which is going to be the, what, max plus 3? Let's see, right, max plus 3. That gives me 22 and 10. Okay. And I take that and multiply it together, right? What is the number of 1 jolt differences multiplied by 3 jolt differences? All right, let's grab our inputs. I think we're ready for this one. So let's return 1 count times 3 counts. Let's change these to longs just in case. We get 1904. Hey, what do you know? Ooh, this looks to have gotten quite a lot more complicated. To completely determine whether you have enough adapters, you need to figure out how many adapters ways they can be arranged. Every arrangement needs to connect the charging outlet to your device. Previous rules needs to connect the charging out. The previous rules about when adapters can successfully connect still apply. The first example above, the one that starts with 16, 10, 15, supports the following arrangements. The charging outlet in your device built-in adapter are shown in parentheses. Given the adapters from the first example, the total number of arrangements that connect the charging outlet to your device is 8. Second example above, the ones that start with 28, 33, 18, has many arrangements. In total, this is a set of adapters that can connect the charging outlet to your device in quite a lot of different arrangements. There must be more than 1 trillion valid ways to arrange them. Surely there must be an efficient way to count the arrangements. What is the total number of distinct ways you can arrange the adapters to connect the charging outlet for your device? Total number of distinct ways. In the first example, all right, so let's grab this first example up here, because this one definitely needs some checking. So what we can do is figure out how many times this is going to branch. So it's kind of like a what, BFT, breadth first search. So every time we come across a difference, oh, this is interesting. So I need to come up with 8, but ideally, without having to do this, go through this a million times. So when we got to 5, we've split off, what, 4 times, right? No, 2 times. 5 to 6 and 5 to 7. So that's what? Power of 2. And then once it got to 6, it could jump to, oh. No, you can't do it just serially. Maybe we should just branch off every time. So we kind of do something like this. And it fits. Let's see. We did a queue. What would this look like? Let me do a quick search. What is a BFT supposed to look like? BFS? All right, and so we would start at 0. We would pull out our current one. And if we can branch, we'll get our neighbors, which would be either a 1 off or a 3 off. Um, can I change this to a hash set? You can't sort a hash set. Why not? How do I get an item out of here? Adapters, get index? No. How about changing our adapters? And just saying it contains current +1 if it contains both a adapter that's 1 away and 3 away, then we want to enqueue I guess we can just do it one at a time. Wait, where am I going? Right. There's probably a much better way to do this. Total is 13, which is not right at all. Oops. Let's see. Total is 21. So we're counting each time we queue up a new one, right? Oh no. We should only be counting if we have a double here, right? Let's see. Let's see, let's verify that we have a +1 and a +2. If it has both a 1 and an adapter 3 away, add to the total. And if it does have these, then NQ it up. So we got a total of 1. That doesn't make sense. Tell me we only split once? What are we at? We're at 4. So yeah, we're splitting up to, we have 5 and 6. Oh, that's because we need to do I guess we need to do this too as well. What am I doing? I'm doing some dumb logic here. We came to a total of 4. Okay. Because we came here, we split twice. Should this be plus equal to? Try this longer input, see how we do. $528. We have a dumb. We should stop saying dumb, but we are not even close to a correct answer. We have gone off the rails here on finding the solution. So we have these arrangements. Why did we get 4 on the first run through? So we're splitting at 0, which does not seem right. So we're currently at 0. We have these should not be correct. It's saying we have both 1, 2, and 3 in our list. Oh, we do. 1, 2, and 3. Oh, I'm checking the bigger list. I need to go back to our smaller one. All right, 4 is when we split. So when we get to 4, we should be adding 5, 6, and 7. Right? Right, 5, 6, and 7. So we've have our queue that has 5 and 7 that now needs to be checked. So we come across 5 and that needs to split. So that's 2 more. Should this always be to the power of 2? Where am I? Where's my total count? Okay. Going blind here. So when we got to this one, we split off 3 times. Why do we... I'm just trying some random things. You need a good way to count the splits. So when we get to 4, we have 3 new paths. So 3, when we get to 5, we have 2 new paths. So that's 3 plus 2. Get to 6, that's 1. Get to 7, that's 1. How do we count this properly? Let's see. I feel like I'm close. So what I'm trying to do here is to kind of do a tree here where, you know, you have one number and then it has, you know, two possible adapters, you know, 2, 3. So now I'm at, you know, 2 paths. So if I have 2 here, I'm adding 2. If I get to 2 and this one has, you know, an adapter 3 and adapter 4, and I get to 3 and this one only has what? Adapter 4. I've created what? An additional 2 paths, right? I mean, I've got 3 paths here. So it's what? It's plus 1 path? How would I know it's plus 1? I mean, I don't count, you know, each of these. So this is 1 path, this is 2 paths, this is 3 paths. So I should have an answer of 3 here. But how do I count this logically? I start with 1, I check that I have 2 paths. So I give it a, you know, plus 2. I get to 2, I see that it has 2 paths. But how? I wouldn't add 2 in this case. Or maybe this should always be plus 1. So maybe I shouldn't be starting at the first one? Because this is more like a first case scenario, and then once I'm here, I really just count the new paths. So if I got here and there's, you know, a 5, the 5 is a new path, the 4 is a new path. So it's more plus 1. Or if it's 3, it'd be plus 2. It'd be something like this. But I need to start. Doesn't make sense. I mean, even if I did this, the this other one would be way off. I'm definitely missing out on a whole lot of paths here. Let's see. Yeah, I basically need to solve this like a 2-year-old here. This is certainly stumping me. So 1 goes to 4. 4 goes to 5, 6, and 7. 5 goes to 6 and 7. Oh, you know, it's probably the way that I'm enqueuing stuff, because no, 6 and 6 should be enqueued separately. Once I get to 6, it's just 7. Once I get to 7, it's just 10. So I have 4 paths here so far. 10 is split off into 2 here. 7 goes to 10. 10 splits off to 11 and 12. Uh, Ten doesn't split. It's weird how they did this one. This splits 11, 12. How should I be counting these? I mean, we're at 1 path here. We're at 3 paths here. 4 paths here. Five paths here. We can enqueue up to 3. If it's any more than 1, we should be adding, yeah, just like I'm doing, 1 extra one. Now, what we should start with is 1 path, right? But I'm getting something fundamentally wrong here. When should I be adding these paths? When I get to the end. Hmm. We've currently have one queued. Then we have 4. Then we have 5 and 7. 7 and 6. 6 and 10. 10 and 7. 7 and 10. Hmm. If we're at the last one, should we be adding a path? Does that make sense? Counting paths. Why are we so far off this number? Every arrangement needs to connect the charging outlet to your device. Previous rules about adapters still apply. So we're checking. It has to be 3 away. Every adapter in your bag. Your adapter list for 3, 9, and 6. Any given adapter can take an input 1, 2, or 3 jolts lower than the rating. Hmm. Doing. Let's see. We're counting. Or should we be multiplying by this number? Taking random stabs in the dark is probably not the best solution. Why are you giving me a 0? Oh. It says... I hope that's not the problem. Oh my gosh. I had the right solution the whole time. I just had a dumb typo. Oh, jeez. Oh, this is eating up CPU though. Oh, I see it's... I might run out of memory before I get the solution here. Why am I using so much memory? Oh, because I'm in queuing so much, I guess? I'm checking every single path. Yeah, this wasn't... If it's taken this long, this wasn't the solution. How else would I solve this without path searching? Or how would I solve this more efficiently? Yeah, I'm certainly putting my computer to work here. I see it's struggling between using close to 20 gigs of memory right now. which is not ideal. So we need to think about this. We're doing a breadth first search. Basically, we're getting to 4, and then we're saying, you know, search everyone for 5, then search everyone for 6 and 7, and then split it off every time. You know, NQ 6 and 7 after you get 5, DQ this one. Kind of like, you know, searching in a spiral around yourself, if that makes any sense. So the breadth first search definitely wasn't it, because we simply just have too many paths to check. It did say that, you know, we had over a trillion paths. So how, when we're looking at the problem, and we got to 4, we split off into 3. Would we... So that, yeah, that's the part that confuses me. I mean, once you get to a number, how would you know further down the line if it's split? I guess it would always split if there's one of these, you know, 4, 5, 6 chains. So would you just... And I guess you can find these by just figuring out where the gaps are. You know, there's a 2-3 gap here. There's a 8-9 gap here. Could you count the gaps? Yeah, I'm gonna go ahead and give up on this solution. My computer could probably brute force that eventually. But yeah, let's try this. Let's take our baby input. Let's comment out this for a second here. Oops. Wrong hotkeys. So let's see, how would I... I want to count the numbers that aren't there. Adapters. Let's change this into a hash set again. We're going to go through each one, I guess, and see if it's there or not. I'm going to be careful with my naming here. having adapters and adapts is probably not the best naming choice here. So we come up with 4 numbers that are missing. If we say 4, I don't know, 4 squared, would that be reasonable? Let's try it with our larger input. I'm glad that this provided both a small and larger input. It certainly helps with debugging. So what do we get for missing? 12? What's the square root of 12? 144? Or the square of 12, I mean. Or should it be 2 to the power? $19,208. Is that a power of 2? Now we're getting into math territory that's not really my strong suit. Okay. So, not a power of 2. So every time we get to a missing number, we split the total number of paths. That would mean it's a power of 2. Hmm. When we came across 4, we split into 3. I guess our missing... Oh, jeez. Our missing is that we don't split. Every time we get across a missing one, we don't split once. We have... This is our large one. We have 12 that are missing over a total of 33. I think we already found out that it wasn't a power of 2. I need to actually think about this because I'm wasting a ton of time. So, what were we trying to do? We were saying that we need to count how many times it splits. This one splits the total of... Let's see, when you get 3 consecutive numbers, you split 3 times. Let's see. So if we split once, if we split, multiply by 2, otherwise multiply by 3, we get a gigantic number. So when we get to 1, we'll count, we'll do nothing, right? One, the total is 1. Or I guess 0. 0 to 1. Total should go up to, should stay at 1. No? Zero. Oh, right. Again, let's go back to our baby input. Well, I was saying we had a pretty good streak of not finding any one that stumps us, but this may be the first one. So when we get to 2, total has suddenly jumped up to 4. Oh. This should just be 1 or 0. I still got showed up with some crazy number. Oh, I guess we shouldn't be counting the ones that aren't there. Why 12? So we check 0, we check 1, we check 4. Now after 4, we should jump to 3, right? 6. Oh, you know what? This is... And this is kind of what we were doing before. Yeah, that can't be right. Yeah, I'm just flailing around right here. I really need to put some thought toward this. When we came across 4, we should have multiplied by 3 to get... multiplied 1 by 3 to get 3. Came across 5, we should multiply by 2 to get 6. No, see, that's the problem. We shouldn't have multiplied by 2. Yeah. Yeah, I don't know. Probably some basic binary tree problem. Let's see, how do you count all possible paths in a tree? Well, it says do a... Well, a DFS traversal instead of BFS? Is that the issue? Hmm. I guess we could try... I guess this is our BFS solution. Our DFS solution would be what we... Hmm. How do you create a binary tree? Pretty sure. I guess it's not technically a binary tree. What would it be? Trinary tree? Ternary tree? What would we be doing? We'd be creating a graph. And we'd be recursively counting paths. Doesn't seem more efficient though. How would we do... How about a DFS solution? What would that look like? Hmm. Now, why is this running so slow? Our sample set, right? Oh no, this is our real set. Our sample set is apparently easy to traverse. Can we speed up our search in any way here? We do this goofy contains thing. Hmm. Just let that run in the background while I think about this. So we're doing a BFS search, which unfortunately creates a huge number of paths and is super inefficient. DFS would create the same amount of work. We need more of a, direct solution, something we could just calculate by, looking at, like I was saying, the missing items or something like that. But I mean, once you split off, you kind of need to figure out like what's at the end of that split. Or are there some, there's got to be some underlying solution here. That helps us figure out what's going on. How would we find the total number of permutations? So we have this set of numbers. And we tell the different permutations by the paths. Do we even need to turn this into a tree? I'm assuming we don't if path searching isn't the answer. How do we figure out unique combinations here? So when we get to 4, we now have 3. But it's not a permutation thing, because you can't just, take this, take 3 and then multiply it by 2 or whatever. You'd have to know that this is only a set of 4 paths. So you'd get 3 and then add 2 or something. Hmm. Maybe you can take... Counting paths in a tree. Hmm. Yeah, it would have been nice if it had some goofy relationship to the number of missing numbers. So we have 0 to 22. And that's what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, then 12 and 13. So we have 13 numbers. 9 are missing. Or is it 10? How many paths? So for 22 numbers, we could split off 22 times, right? Or is it 21? Somehow, somehow we need to reduce that to only 8. But it's not a binary tree, though. How would you count the arrangements? Hmm. this be combination? Can I make this into a combination problem? How do you do a factorial? Let's see, it's HR factorial. I can write a program? What is the factorial algorithm? N factorial divided by n minus k factorial. Or I guess just factorial. Can you maybe count every consecutive number? 1, 2, 3, 4, 5, 6. What's 6 factorial? Well, it's definitely not 8. We wouldn't have it. What is the other one? It's combinatronics? No, that does make sense. 8 wouldn't be a solution for permutation like that. Hmm. Or would it? Hmm. Number of arrangements into compartments. Hmm. Total number of options. R would be the number of how many items you need to choose. Let's see if Wolfram can help me here. Hmm. How many was in this one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See. Can I turn this into a permutation? How would I figure out what options are available? Yeah, this one may have to call it quits. We are at the almost 2 hour mark. I haven't really found a viable solution here. Yeah, it's not path searching. At least I don't think so. If it is, the paths are ridiculous. If it is a permutation problem, how do we figure out what our options are? When we come across 4, we get 3 options. No. Yeah, I'm not sure how you'd turn that into permutations. Hmm. Hmm. Seems like it'd be a weird. Could you turn this into a path problem? And I'll give this 5 more minutes, see if I can figure out some weird solution. Then I'll call it a day. Hmm. This arrangement. Hmm. Let's see. You know, I wonder if this 1 in 3 jolt difference thing was a big deal. There are 22 1 jolt differences and 10 3 jolt differences. Hmm. That's not a power of 2. 22 and 10. How many? 10 3 jolt differences. Hmm. Yeah, doesn't make any sense. I'm not sure what I'm trying to do right here. Twenty-two 1 jolt difference and 10 3 jolt differences. Yeah, I think that's it. I'll have to, unfortunately, I'll have to come back to this one some other time. It's a shame, but what can you do? Alright, that's it for this one. Hopefully I'll have the solution before tomorrow's starts. Yeah, this one's a shame. Oh well, that's it for this one.